Welcome friends, welcome to our YouTube channel Crystal Learning. A very warm welcome to all of you. So today we will learn the concept related to the subject fluid mechanics. Let's read out the question. This question came in Engineering Services Examination Mechanical 1998. A little bit old. That's why because of the options given in this question in many previous years books are wrong. The option is given 4W because they copy from each other. So if a mistake is done in one book, then this goes on in other books also. But in few references, you will find the right option, that is 3W. So today we will prove this. So let's read out the question. Question is saying a cylindrical piece. So it is saying that a cork is there and shape is cylindrical. Okay. First information. Weight given is W. Weighing W. Float weight is axis in horizontal position. This is the axis. So it is floating like this. In water, it is floating like this. Axis horizontal. In a relative liquid density 4, this liquid relative density is given RD equal to 4. By anchoring the bottom, the cork piece is made to float at neutral equilibrium position. Another important information given in the question. With its axis vertical. Now it has to float at neutral equilibrium position, and that too its axis has to be now vertical like this. Okay. So vertically downward force exerted by anchoring would be. So just wait for a while. We will make this the terms and condition of these questions more clear as we go ahead. So let's study some concept. So first thing, it is talking about neutral equilibrium position. So that means it is talking about stability. So stability is of three types, that is stable equilibrium, unstable equilibrium and neutral equilibrium. So equilibrium positions are defined on the basis of 2 points, that is center of buoyancy and center of gravity. So center of buoyancy is that point on which that buoyant force will act, and center of gravity is that on which that mg, that is weight of the body, will act on center of gravity. So we have taken a rod and we have made the bottom heavy. So we know that that G, that is center of gravity, will move towards that area where the mass is concentrated. So it will come down. So this is the position, initial position. So in this case, center of buoyancy is above center of gravity, and we are giving a rotation in anti-clockwise direction. So we will see what is happening. So when we rotate this rod in this direction, we see that G will act downward direction, that is mg weight, and center of buoyancy will act in upward direction, and this is creating a couple, that is stabilizing couple. So it will rotate again to its initial position. So this is known as stable equilibrium. So now stable equilibrium is clear. Second case is top is heavy, so that G will shift in upward direction. Now that G will be above center of buoyancy. So again we will disturb this anti-clockwise, rotate some anti-clockwise direction. So this case we will see that G is acting downward and center of buoyancy is acting upward. So it will destabilize the couple. Now it won't come back to its original position. It will get destabilized. So this type of condition is known as unstable equilibrium. Okay. So now we will see what is neutral equilibrium. So neutral equilibrium is if weight is removed, this weight is removed and the bar is made heavy enough to become completely submerged. So we are completely submerging it, the body, so that what will happen when there will be complete submerged. So the weight of buoyant force are balanced, and then its center of gravity and center of buoyancy will coincide. Just see this case. So in this case it is completely submerged and these 2 points are coinciding. Now you just give a anti-clockwise rotation, a couple. So it will be in this position and it will stay in this position, new position. Okay. Because in this case also center of buoyancy is upward direction and G is acting downward, it is balancing. So neutral equilibrium will balance in new position, it will stay in new position. So this is known as neutral equilibrium. Important point we have to note down here is we have to completely submerge so that the center of buoyancy and G is coinciding. So this is all about neutral equilibrium. Now we will study Archimedes principle, because the first case it was saying that cork is free floating in a liquid of relative density 4 with its axis horizontal position. So Archimedes principle says an object wholly or partially immersed in liquid will subjected to an upward force. Whenever you submerge any body in water or any liquid, there will be an upward force acting on that body, that is known as upthrust. That will be equal to weight of fluid it has displaced. Okay, or when a body is immersed or partially in the liquid, it experiences a apparent weight loss which is equal to weight of liquid displaced. Whenever you weigh a body in air, it will tell the true weight, but whenever you weigh that body inside the water, like in this case, so it seems quite less, that that weight of the body decreases, there is a apparent loss. So what is that? When you submerge this body inside the liquid, so downward force is weight of the object, that is W, that will act downward direction. Upward force will act, that is known as upthrust, and that will be equal to the weight of displaced liquid. Whatever liquid it is displacing, this volume of liquid it is displacing, so that will be equal to upthrust force. Initially this is what the level of water, but after submerging this body, that volume will rise. Okay, and this is equal to U. So this volume of water it has displaced, so that reading will be in this case W minus U. But in free floating condition or flotation principle, when a body is floating freely on water or any liquid, then downward direction acting is W and upthrust force is U. That is balancing. Okay, that's why it is able to float, otherwise it will drown. Okay, so in floating condition W is U. This condition you have to note down. Okay, so what happens when you completely submerge any body inside a liquid? What happens? A condition will come, that is relative density. A formula will be there. Let's see that formula. Let W1 is weight of substance in air. W2 is weight of substance when it is completely immersed in water. Okay, and W1 minus W2 will be apparent loss in weight. Whatever loss in weight, it is this condition, W minus U. Okay, so weight of water displaced, what will be the apparent weight loss in substance in water will be the weight of water it has displaced, U. Okay, so here the volume of water displaced is equal to volume of substance. If it is completely submerged, so whatever volume of the body is there, that equal volume of water it will be displacing. Okay, so that statement is written here. So relative density is defined as weight of the body in air divided by apparent loss of weight in water. So here we will see W1 was weight of body in water and apparent loss is W1 minus W2. For example, a piece of cork weighs 8 Newton in air and weighs 5 Newton in water. When same piece is submerged in water, it weighs 5 Newton. So weight of water displaces is thus 3 Newton. So what will be the weight of water it has displaced? That will be the difference of this two values, apparent loss W1 minus W2. So 3 Newton. So here we get weight of rock divided by weight of same volume of water, or apparent loss, whatever you say, both terms are equal, that is 8 by 3 equal to 2.7. So thus density of rock must be 2.7 times of density of water, that is relative density of rock. So we have defined relative density like this. So that means that density of water is given 1000 kg per meter cube, then rock must have a density 2.7 into that density of water, that is 27000 kg per meter cube. So this is the formula of relative density. Remember this formula also if you want to calculate the relative density of solid. So now as a general rule, relative density will be given by weight in air divided by apparent loss of weight in water. Again in properties of fluid we have studied relative density is also known as specific gravity. Okay, so that is defined as ratio of mass density of fluid to mass density of standard liquid, and standard fluid is water here. Okay, so let's see a diagram here. So initially it was saying that it is floating with its axis in horizontal means horizontal. Okay, its axis is horizontal. This is the cylindrical piece. Okay, its axis is this xx. So it is in horizontal direction, and in final direction it is in vertical direction. Okay, this axis is vertical direction. So it is saying that initially when it is floating, so some part of the volume will be in the liquid and some part will be above the liquid. That's why it is floating. But it is saying that it has to be in neutral equilibrium. So for neutral equilibrium, we have to completely submerge this body, and that too one condition is there. We will be submerging this body completely with keeping its axis in vertical direction. So it is free floating in this condition with this excess volume above the water. So when you will be pulling down this body to keep this in neutral equilibrium, you have to keep an anchor, okay, like a ship. So you have anchor, you have to pull down this body downward. So when you will be pulling this body downward, this extra volume when it will be getting inside the water, so we know that buoyant force will be acting against this. So this anchor force which is acting vertically downward is equal to this buoyant force which is acting upward, because we have submerged extra volume inside this water. So we will now see that in free floating condition how much of volume is inside the liquid and how much of the volume is outside the liquid. Okay, so let's see the formula. So in the floating condition, free floating condition, weight of solid is balanced by upthrust, and upthrust is equal to weight of liquid displaced. So this formula becomes weight of solid is mg, and mg is volume of body into density of body into g, and that is equal to upthrust equal to volume of liquid displaced into rho of that liquid into g. Now we are just rearranging this term. We are keeping volume of liquid displaced at one side of equation and other side all the other components. So V of liquid will be divided here. Okay, so rho of body is there, rho G will be cancelled. So no need to worry for that. Here we are doing rho of water multiplying and divide. Okay, so there is no no effect, but we get one thing, that is rho of liquid divided by rho of water becomes relative density. So this term becomes volume of body divided by relative density of liquid into rho of body divided by rho of water, means whatever volume of liquid displaced is given by this formula. But if we want to see the what proportional volume is above and downward, so then we assume or it is there, because when you fix the body, that is rho of body is constant. When you select, that is suppose steel is there, so rho of body is constant and water density is constant, it is not varying, so we can take this as constant. So in this equation we can use a proportionality sign, that is V of liquid is directly proportional to volume of body divided by relative density of liquid. So this formula we got, and just pay attention, that is it is proportionality, not equal to is this equation 2. If you want a total exact volume displaced, then you have to use equation 2, but we are here seeing this proportionality, so to get an idea. So in this figure we got an idea, because relative density is given 4, so this will become V of body divided by 4, means that in free floating condition, in this condition V by 4 is inside the volume and 3 by 4 is outside the volume, because total volume is equal to V. So now we have to submerge this 3 by 4 volume, extra 3 by 4 volume inside the water. That will give rise to buoyant force, and that buoyant force, indirectly we have to calculate that buoyant force, because it won't go inside this liquid by itself. We have to put a force in downward direction to submerge this, and when we are submerging this, so this value is equal to the buoyant force. Okay, so now I hope this is clear. So volume of liquid displaced is V by body divided by 4 into rho of body, rho of water. Okay, so now the cork is made to float in neutral equilibrium with its axis as vertical. So we see that 3 by 4 V of body into rho of body divided by rho of water. This is the total volume V is outside the liquid. Thus, center of buoyancy and centroid will not coincide. But in the question, it is saying that we have to float this body in neutral equilibrium position, and in neutral equilibrium position, centroid must coincide with center of buoyancy. For that, we have to completely submerge this body. So we have to just submerge this extra volume inside. Okay. So this extra volume is 3 by 4 volume of body into row of body into row of water. So indirectly we have to calculate this upthrust force. So this vertical downward force will be equal to upthrust force when this remaining body is submerged completely. That is 3 by 4 volume of body into row of body, row of water. So using equation 1 says upthrust value. Let's revise this equation first. So upthrust is saying equal to volume of liquid displaced. You have to just see this part. Okay, this part. Upthrust is volume of liquid displaced into rho of liquid into G. So here we know the volume of liquid displaced is 3 by 4 volume of body into rho of body upon rho of water into rho of liquid into G. Now we just rearrange this term. 3 by 4 rho of liquid and rho of water at one side multiplied by volume of body into rho of body into G. Rho of liquid upon rho of water is relative density, that is 4, and volume of body into rho of body into G is mass into G, that is weight of the cork. So 3 by 4 into 4 then into W. 4 gets cancelled and answer is 3W. So this is the upthrust force, or you can say the downward force you have to put to keep that extra volume inside the water. So 3W is the right answer. That vertically downward force exerted by anchoring or upthrust or weight of liquid displaced for this amount of volume is 3W. I hope you enjoyed this explanation for this question, and now all the doubts are clear for this question. Thank you for watching the lecture. Meet you in the next lecture with a new question and with a new concept. Till then, have a nice day.